Hi, this is Abhiram from Purdue School of Engineering. Today, I'm going to be talking about our paper on how we can train a single denoiser for multiple noise levels. When we're training a neural network for estimation tasks such as denoising, we usually train a different denoiser for different noise levels. For example, here, we train a denoiser for a noise level of sigma equal to 5, another for sigma equal to 50, and one more for sigma equal to 100. A blind denoiser is a network which can take as input an image with any noise level and produce the corresponding denoised image. When we are training a blind denoiser, we usually draw samples uniformly across all the noise levels and use them as input. Let us take a look at the peak signal to noise ratio performance of such a denoiser. The Psnr plot looks something like this. Compare this to a network that is trained at one particular noise level. This network performs extremely well at the noise level at which it's trained, while the blind denoiser performs well at almost all other noise levels. Now consider a huge set of these denoisers that are trained at every noise level. If we combine all these denoisers, we get this black curve, which we call as the ideal Psnr curve. This is called the ideal Psnr curve because this is the best performance that we can get out of the network at every noise level. Now look at the difference between the ideal PSNR curve and the uniform distribution curve. You can see that the difference is smaller when the noise is heavier, the difference is much larger when the noise is weaker. Now what if we want a network that gives a more consistent performance? Note that consistent here does not mean that the PSNR is same across all the noise levels, but rather the difference between the ideal PSNR and the network is consistent. The goal of this paper is to show how to train such a network, or rather, how to come up with a training distribution with which we can train this network so this performance can be achieved. To solve this problem, we propose two solutions. But before we go into the solution themselves, let us formulate this problem more formally. We have a green signal Y, which is getting corrupted by a noise of strength sigma. Now that this is a denoising example. For most of this paper, we are going to use denoiser as an example. But the framework which we are developing is much more general and it could be used for any kind of image degradation. We show another example here where we want to deblur a blurred image. For this example, sigma could mean the radius of the blur. We want to find a function f which can take an image which is degraded by any noise of strength sigma and produce the corresponding denoised image. We are going to look at learning-based approaches, and therefore neural networks are going to be a part of this. We define two distributions. We denote the testing distribution by P of sigma. This is where the noise samples are going to get sampled when we are actually using the network for denoising or when we are testing the network. For example, here we assume the testing distribution is uniformly distributed across all the noise levels. The next one is the training distribution denoted by pi of sigma. This is where the samples are going to get sampled when we want to actually train the network so that we can give some kind of performance guarantee. We already know the testing distribution and we want to find the training distribution. We define the risk function, the overall risk function R of f by this equation. We already know what P of sigma is. It is the testing distribution. We define R of f given sigma as the conditional risk. It is defined as the expected value of loss at one particular noise level. If you recall the PSNR curve, R of f given sigma will be the PSNR at a noise level of sigma, or more specifically, the mean square error at a noise level of sigma. So the overall risk is nothing but the weighted average of the conditional risk over all the noise level which we are considering. We define the function f pi as a network that is trained with a distribution of pi of sigma. Note that pi of sigma need not necessarily be P of sigma, which is the testing distribution. So therefore, we may have two different PSNR curve when we are training with P of sigma or pi of sigma. We define the function f delta of alpha as a network that is trained at one particular noise level of alpha. and we define the ideal PSNR curve by R of f delta given sigma. With that, let us go into our first solution, which we call as the minimum guarantee problem. We start the definition of this problem by minimizing the overall risk. Note that if we don't add any other constraint to this problem, then the solution to this problem is nothing but training the network with the testing distribution P of sigma. But we add a constraint which controls the worst case difference between the ideal PSNR curve and the network. Let us take a closer look at what this equation means. We start with the ideal PSNR curve. We say that the conditional risk curve, which is given by the network, should always lie within an epsilon gap from the ideal PSNR curve. For example, this red line doesn't satisfy this constraint and therefore is not a feasible solution, while this green curve is. To solve this problem, we look at the dual of this problem, for which we first write down the Lagrangian. Let us say we are able to find the dual solution, which is denoted by lambda star. Now, to find the corresponding primal solution, we plug this dual solution into the Lagrangian and minimize the Lagrangian with respect to the function f. Let us take a closer look at this equation. Note that the minimization is over the function f, and the second term doesn't depend on f, and therefore we can ignore it. We can write the term p of sigma plus lambda star of sigma as some other distribution pi star of sigma. We can do this because lambda is always greater than 0, and therefore by normalizing this by the sum taken over all the noise levels sigma, we can get some other distribution pi star of sigma. So once you know what the dual solution is, you can come up with a distribution pi star of sigma with which we can train the network so that we can get the solution to problem 1. Now, of course, we don't know how to get the dual solution, for which we propose a dual ascent algorithm. This algorithm consists of 2 steps, which we perform iteratively till the algorithm converges. Now let us take a closer look at what these 2 equations actually mean. We start with a sampling distribution with which we train the network. Once the network is trained, we plot the corresponding conditional risk curve, based on which we update the Lagrangian multiplier lambda, which then updates the sampling distribution, and then using this we train the network again. We keep repeating this process till the algorithm converges. Now this algorithm works fine, but it has a couple of drawbacks. The first one is that it depends on the choice of epsilon. If you choose an epsilon which is too small, then there may not exist a solution to this problem, and therefore the algorithm doesn't converge. The second one is that the solution depends on your knowledge about the testing distribution. If you have no idea where the noise samples are going to come from, then you cannot run this algorithm. To deal with this, we propose our second solution, which we call as the uniform gap problem. It is defined by this equation. To understand what this equation means, again, we start with the ideal PSNR curve. Now let us say we have the conditional risk curve which is given by the network. We find the maximum difference between the ideal PSNR curve and the conditional risk curve. And then we want to minimize this difference. This problem is called the uniform gap problem because as you keep decreasing this maximum difference, you end up with a solution which has uniform gap across all the noise levels. An added advantage of this problem is that it gives you the epsilon star, which is the minimum epsilon which you can use for your problem 1. The algorithm to solve this problem is exactly similar to the algorithm which we used for problem 1 with a small modification on how we are updating your lambda. Now let us compare problem 1 and problem 2. Problem 1 still minimizes the overall risk, but it controls the worst case difference between the ideal PSNR curve and the conditional risk curve given by the network. While your problem 2 doesn't depend on your overall risk at all, but rather it just minimizes the worst case difference. So that means your problem 1 is going to depend on your choice of testing distribution, while your problem 2 is not going to depend on it at all. So therefore, you can have multiple solutions for problem 1, while there is always going to be one single solution for problem 2. Now, which of these two is better? It will depend on your application and also how much knowledge you have about your testing distribution, P of sigma. With that, let us look at some results. We do our experiments on the DNCN and Denoiser. We divide the noise level from 0 to 100 into 10 discrete blocks so that the computation is easier. We also plot the PSNR difference instead of the actual PSNR so that the visualization is easier. Of course, the ideal difference is where we have 0 dB difference between the ideal PSNR and the conditional risk curve across all the noise level. We know this is not possible with one single neural network. For our first example, we choose a testing distribution which is uniformly distributed across all the noise level. The corresponding PSNR difference curve looks like this. You can see that the difference is almost 1 dB at the lowest noise level and almost 0 at the highest noise level. For problem 1, we choose an epsilon of 0.4 dB, and our algorithm gives this as the distribution, and the corresponding PSNR difference curve looks like this. You can see that the PSNR difference is always smaller than 0.4 dB. You can see that the algorithm is playing a trade-off game where it reduces the PSNR difference from 1 dB to 0.4 dB at the lowest noise level, while the PSNR difference increases by a small amount at the highest noise level. Now let us take a look at another example where we assume all the noise samples are coming from a noise level of sigma equal to 25. The corresponding PSNR difference curve looks like this. Now I want to note here that if you're 100% sure that all your samples are going to come from sigma equal to 25, you need not do anything else. But if there is going to be an occasional sample that is going to come from some other noise level, then you may want to run our algorithm 1, which gives this as the distribution and this as the corresponding PSNR difference curve. Note that again here you can see the algorithm is playing a trade-off game where it trades off the performance at sigma equal to 25 by a small amount to make sure that the network isn't performing too badly at all other noise levels. With that, let us go into our second solution. As I've already noted, there is only one solution for this, and the distribution looks like this. The corresponding PSNR difference curve is looking like this. You can see that the difference is almost fairly uniform across all the noise level of about 0.2 dB. Now, I want to note here that if you can run our algorithm to any neural network which you want. But if you don't want to run, we propose a rule of thumb distribution which we call as the 80-20 rule. We call this distribution the 80-20 rule because most of the sample distribution is at the lowest noise level, and the rest is coming from all other noise levels. With this distribution, we trained 3 networks, and you can see that the performance is fairly uniform across all the noise levels. With that, let me summarize the contribution that we have made in this paper. We propose 2 problems. Both these problems are about finding an optimal sample distribution such that we can give some kind of performance guarantee on our networks. Both these problems are equivalent to playing some kind of minimax game on the overall risk. Both the problems are convex in most of the cases, and we have proved this in our paper. The algorithm which we have proposed to solve this problem is a dual ascent algorithm, and therefore it is guaranteed to converge irrespective of whether the problems themselves are convex or not. Now let us compare our problem 1 and problem 2. Problem 1 requires your knowledge of the testing distribution, while your problem 2 is agnostic to the testing distribution. Problem 1 minimizes the risk with respect to a constraint epsilon, while problem 2 minimizes the worst case risk. It is better to use problem 1 if you have a rough idea of what the testing distribution is, and it's better to use problem 2 if you have no idea where the testing samples are going to come from. And therefore, your problem 2 is going to give a more conservative result. Thank you.